Welcome to this video on the derivative of a vector function. I'll start with the definition of the derivative of a vector function at a point. I'll then explain this definition using examples. The derivative of a vector function at a point can be defined as follows. A vector function r of t equal to f of t I plus g of t j has a derivative at t if the functions f of t and g of t have derivatives at t. The derivative is the vector function r prime of t, written r apostrophe left bracket t right bracket. We can also refer to this derivative as dr dt. This derivative is equal to the limit of r of t plus delta t minus r of t over delta t as delta t approaches 0. And this is equal to df dt I plus dg dt j. I'll now explain this definition using the following example. I'm going to use a vector function to describe the position of a moving particle. Shown to the right is a particle moving in the xy plane during a time interval. We can describe each of the particle's coordinates as a function of a third variable, t. We can describe the particle's position on the x-axis as a function of time using the equation x equals f of t. And we can describe the particle's position on the y-axis as a function of time using the equation y equals g of t. For values of time t on the time interval I. The points x, y equal to f of t, g of t for values of time t on the interval I form the curve in the xy plane that is the particle's path. We can describe the particle's position at time t as the point P. The vector r of t from the origin to the particle's position P at time t is the particle's position vector. We can describe the position vector in component form as left angle bracket f of t, comma g of t, right angle bracket for a given time t. The functions f of t and g of t are the component functions of the position vector. We can also express the position vector at time t as f of t I plus g of t j for a given time t. This expresses the position vector as a linear combination of standard unit vectors I and j. This equation, now highlighted, defines r of t as a vector function of the variable t on the interval I. The vector function r of t assigns a position vector to each value of time t on the time interval I. We can think of the particle's path during the time interval I as the curve traced by r during this time interval. The component functions of r of t are f of t and g of t, and in this example, both f of t and g of t are differentiable functions of t. At time t, the particle is at position P. At time t plus delta t, the particle is at position Q. Between time t and time t plus delta t, the particle undergoes the displacement delta r. Delta r is a displacement vector, which is now shown to the right. The displacement vector delta r is the directed line segment PQ. The sum of the position vector r of t and the displacement vector delta r is equal to the position vector r of t plus delta t. If we subtract on both sides of this equation by r of t, we get that the displacement vector delta r is equal to r of t plus delta t minus r of t. The displacement vector delta r is equal to the difference between the particle's position at time t plus delta t and the particle's position at time t. So far, we have that r of t is equal to f of ti plus g of tj, and that the displacement vector delta r is equal to r of t plus delta t minus r of t. We can express this displacement vector delta r in terms of the component functions f of t and g of t. When we do this, we get that delta r is equal to left bracket f of t plus delta t I plus g of t plus delta t j, right bracket, minus left bracket f of t I plus g of t j, right bracket. Here, I'm expressing r of t plus delta t as left bracket f of t plus delta t I plus g of t plus delta t j, right bracket, and I'm expressing minus r of t as minus left bracket f of t I plus g of t j, right bracket. This expression, now highlighted, is equal to left bracket f of t plus delta t minus f of t, right bracket, I, plus left bracket g of t plus delta t minus g of t, right bracket, j. So we have that delta r is equal to left bracket f of t plus delta t minus f of t, right bracket, I, plus left bracket g of t plus delta t minus g of t, right bracket, j. As delta t approaches 0, the point Q approaches the point P along the curve. And as delta t approaches 0, the secant line PQ approaches a position tangent to the curve at P. And also, as delta t approaches 0, the quotient delta r over delta t approaches the limit, left bracket, the limit of f of t plus delta t minus f of t over delta t as delta t approaches 0, right bracket I plus left bracket, the limit of g of t plus delta t minus g of t over delta t as delta t approaches 0, right bracket j. This limit, now highlighted, is the derivative of the function f of t with respect to t. And this limit, now highlighted, is the derivative of the function g of t with respect to t. So delta r over delta t approaches the limit df dt I plus dg dt j as delta t approaches 0. df dt I plus dg dt j is the derivative of the vector function r of t. We can refer to this derivative as r prime of t or dr dt. The derivative r prime of t at time t is now shown on the diagram to the right. As delta t approaches 0, the vector delta r over delta t approaches a position that is tangent to the curve. R prime of t is a vector function which assigns a vector to each value of t on the time interval I at each point where the derivative exists. When r prime of t is not equal to the 0 vector, it is tangent to the curve at each point where the derivative exists. This brings us to a definition for the derivative of a vector function at a point. A vector function r of t equal to f of t I plus g of t j has a derivative at t if the functions f of t and g of t have derivatives at t. The derivative is the vector function r prime of t. This derivative can also be referred to as dr dt. This derivative is equal to the limit of r of t plus delta t minus r of t over delta t as delta t approaches 0. And this is equal to df dt I plus dg dt j. I'll now demonstrate how to calculate the derivative of a vector function in an example problem and solution. In this example, the vector function r of t equal to f of t I plus g of t j is equal to t squared I plus 3t j. The derivative r prime of t is equal to df dt I plus dg dt j. the function f of t is equal to t squared. df dt, the derivative of f of t with respect to t, is equal to 2t. So df dt I is equal to 2ti. The function g of t is equal to 3t. dg dt, the derivative of g of t with respect to t, is equal to 3. So dg dt j is equal to 3j. I've just calculated that the derivative r prime of t is equal to 2ti plus 3j. To summarize, in this video, I've explained the definition of the derivative of a vector function. I've also demonstrated how to calculate the derivative of a vector function in an example problem and solution. If you found this content useful, please subscribe to the channel to receive more content. Thank you very much for watching this video. See you next video.